So, today we will learn about the electrical or electronic properties of solid. Electronic properties of solid. So, this is one of the very important properties of solid. So, depending on the electrical conductivity or resistivity, the solids can be divided into three categories. One is conductor or metal, another is semiconductor, and third category is insulator. So, insulator is very high resistance, its resistivity is very high, conductivity is very low, whereas metal have very high conductivity, low resistivity, and semiconductor is basically in between. So, its conductivity is higher than metal, but lower than the insulator. Okay. So, we will try to find out the origin or reason behind such behavior of different materials. So, today we will discuss about the metal, conductor, what is the origin of this electrical behavior of this metal. So, metal or conductor. Okay. So, metal conductor, it obeys Ohm's law. So, this is the one important phenomena, that it obeys Ohm's law. And it shows very high electrical as well as thermal conductivity. So, very high electrical and thermal conductivity. And its when we study any property of any solid, So, we use external parameter and apply on that material and see the response of that material to that parameter. So, what are the external parameters? External parameters one is temperature, T. So, behavior of a material with temperature. So, that generally we observe to study that material, and other one is electric field. We apply electric field on the material and see the response. Third parameter, important parameter, is magnetic field. What is the response of that material to magnetic field? And fourth one is it's light. If you put light on the material, what is the response of that material? So, to study behavior of material in different aspect, it may be thermal, it may be electrical, it may be magnetic, it may be optical. So, we have to use this external parameter and apply on them and see what is the behavior of that material in response to that external parameter. So, here, so this Ohm's law, basically here we apply external parameter electric field, right, and electrical conductivity, basically it comes from here. So, for electrical conductivity, one has to apply electric field. For thermal conductivity, one has to apply temperature, external temperature one has to apply, or one has to vary the temperature and see the response of that material, right. So, this resistivity of this material, metal, basically its behavior at low temperature and at above room temperature is different. So, generally above room temperature, it is proportional to T, but at low temperature, so this is room temperature and above. Of course, this temperature it is decided, it is not independent of material, it depends on material, and that critical temperature, it depends on that material. So, these are generally this happens, it is not always true for all material, but at low temperature generally it varies with the power of 5, T to the power 5, and is at low temperature, right. So, if material is pure or material is impure, means some impurity in that material is there. So, depending on that this resistivity, it generally it has two part. It has two part. So, this one part is independent of temperature, one part is independent of temperature, it is all the time it is there. Internal, we tell this internal resistivity, and this another part is there, it depends on temperature. Okay. So, this type of resistivity of a metal generally for this, if it is having impurity in that metal, so it's behaves like this. Okay. If not, impurity is not there, then it is rho T. So, this part comes from this basically impurity. So, these are the experimental fact, it is seen, it is this type of behavior is observed from metal, and this response to this magnetic field of the metal, that also it is there. So, it is called so variation of resistivity with magnetic field. So, here variation of resistivity with temperature. So, similar type of variation of resistivity with a function of magnetic field, that is also it has a response to the magnetic field, and it is generally called magnetoresistance. Okay. So, due to magnetic field, why resistance changes, what is the reason, and how it depends on the magnetic field. Okay. So, that is basically in terms of magnetoresistance or magnetic resistivity, we express them. Another important phenomena metal shows, and that is called Weidmann-Franz law. Weidmann-Franz law. Weidmann-Franz law. So, that is basically the ratio of the thermal conductivity, and electrical conductivity, it is proportional to temperature T. It is proportional to temperature T all the time, this ratio is proportional to T. So, this equal to some constant into T. So, this type of behavior all metal shows. Okay. So, these are the feature of metal. So, our task is here to find out the origin of these properties, why it shows, why it behaves like this, why it behaves, how it behaves to electrical field, temperature, magnetic field, right. So, these are the tasks we will explore in this lecture. So, let us see how we can explain this behavior. So, for that we have to know about electronic structure of the metal, because electrical or electronic property is basically it depends on the electronic state or electronic distribution in the metal. So, already we have mentioned earlier that metallic bond, in case of metal, that metallic bond what we have seen, basically alkali metal, it is the ideal example. So, in case of sodium we have we have seen that it's sodium ion, sodium plus and 1 electron. So, this in metal they are in solid in crystalline form. Now, each sodium it gives 1 electron in the system, right. So, we have many sodium atoms in the crystal. So, we have many electrons. So, these electrons are basically they can move throughout the crystal, throughout the solid, right. Right. So, the sodium atoms hold in a crystal due to metallic bond. So, that metallic bond is basically this as a whole, these electrons can move in the crystal, and that so electrons is negative charge, and these ions, these are positive charge. So, these are as if these are heavy positive charge is there, and now these electrons moving around them. So, it is so a particular electron is not attached with the one ion. So, they are sharing this, they are sharing with all the ions. So, that is basically, so as a whole, these whole electrons are held by this whole sodium ions. Okay. So, this bonding, so holding each other, not individually one ion one electron, as a whole, that whole electrons and as a whole ions. So, they have some weak interaction, electrostatic interaction, and that type of holding is basically called metallic bonding. So, that is we have mentioned earlier. So, now to explain all the properties whatever I have mentioned, this response to electric field, magnetic field, temperature. So, this, one has to take model, and then based on that model we have to assume, we have to speculate, and based on that model we have to derive relations, and that relations whether it can satisfy the experimental result or not, that one has to check. If it satisfy, then we demand that the assumption in model for that model are correct. Okay. So, to explain all these things, this one model, very famous model was taken, that is free electron gas model. So, this model is basically given by Drude. This model was given by Drude, that is why it is called Drude model or free electron model. So, this is also called Drude model. Or free electron model. Okay. And French was having some contribution also to this model. So, what is that model? So, that we will try to explain. So, we have a piece of metal, we have a piece of metal we have a piece of metal. Now, it is made of either sodium or this copper or silver, gold, whatever it is. So, it is considered that since these electrons are very weakly interacting with the ions. So, in this model, this weak interaction is ignored and considered that in this metal these electrons are free, Okay. Okay. Although sodium, say if I just take as a example sodium, so that ion, positive ions are there, so equal number will be right. Okay. So, both are there, electrons and ions. Ions are fixed in the site, right, as lattice structure, according to the lattice structure they are fixed in the sites, right. Now, these electrons, they are free, there is no interaction with these ions. So, that is ignored, and now in a piece of metal, now we have free electrons. So, they can move anywhere, but restriction is that this electron cannot go out from the metal. this electron cannot go out from the metal. So, because we have not seen any electron emission at room temperature, right. If we increase the temperature for any material, metal, so electrons emit. So, there is a thermal emission, but so at in normal temperature the electrons are not allowed to go out and they do not go. So, it is assumed that the potential energy of electron inside the metal, it is constant and it is low, and outside of the on the metal or on the surface of the metal and outside. So, this potential energy of a electron, if one electron is here, potential energy of that electron is very high compared to the electron inside the metal. So, it is assumed that the potential energy outside is like infinity, is very high, and inside of the metal this potential energy is very low. Okay. So, potential energy inside the metal, it is very low. So, that is considered as a 0. Potential energy of these electrons inside metal is 0, and outside metal just on the surface and outside of the metal, this potential energy is very high. So, it is taken as say infinity. So, it is like a just potential box, you know. So, this electron are in a potential box. So, inside it is potentially 0, but it cannot cross the surface, that is the potential barrier, very high barrier, it cannot go out from the from that box. Okay. But in that box it is free to move in all directions, it has no potential energy, it is considered as a 0. Okay. So, this is the model, free electron model or Drude model. So, all metal is considered that it has a free electrons, it has a lot of free electrons, and it behaves just like gas of atoms, molecules, right. So, whatever the kinetic theory of gas so that will be applicable to this free electron gas. Okay. So, it is also assumption that this free electron, it will just behave like gas. So, whatever the theory is applicable for gas, so that will be applicable for this electron gas in case of metal. So, this is also another assumption. So, now in case of gas, you know this, when they are moving and they collide with each other. Okay. So, there will be distribution of velocity of gas, there will be distribution of energy of the gas, right. So, here if I consider that energy of this of electron gas, for each electron it will have only kinetic energy, if its velocity is v, like from that kinetic theory one can, so this kinetic energy half m v square. So, that is the energy of each electron, and from kinetic theory one can write that this energy is basically 3 by 2 a b t, Boltzmann constant, this is temperature. So, from kinetic theory, so we can apply on this electron gas and we can write this, right. So, now if we apply electric field, then what will happen? If I apply electric field, so then now they are free. Before applying electric field, they are free, they are moving in all directions. Now, when I will apply electric field, so I am applying in a particular direction, I apply electric field, I am applying in a particular direction, right. So, now they will move in that direction, right. So, why they will move? Because force is acting on this electromotive force, right. So, that electromotive force, because of electromotive force, now that electron will feel force. If electric field is E and charge is small e, so this will be the force acting on a electron. So, because of this force, it will move, it will be accelerated. When force is acting on a particle, so it will be accelerated, right. So, then to find out, one can apply Newton's law. So, this we can equate with mass into acceleration, right. So, from this one can find out the acceleration A equal to E by m. So, m is mass of electron and capital E is electric field, right. Now, because of this force they will move, when they will move, so there will be some collision, although its collision is very less in number, but it has some collision. So, that we express in terms of mean free path lambda, mean free path is lambda, right. And if it is moving with velocity v, so then time this lambda by t, that is velocity. So, now by velocity, that is t. So, this lambda is called mean free path, okay, means path between two successive collision, right. So, after one collision, so it start fresh movement, fresh velocity, and it goes to the travel lambda distance and then gets another collision. So, this distance is basically its lambda and it is called mean free path because it is average one. It is for all the collision for all electrons is not same. So, this is the one has to take average and this. So, this is the time, during this time it does not during this time it does not collide. So, this tau is called relaxation time, it is called relaxation time. Okay. So, basically due to this force there will be acceleration, and this acceleration A. So, due to this force it will travel say distance s, if its acceleration A, and if we consider it starts from 0 velocity and moving. So, then we can write s equal to the distance A t square. Okay. So, at time t what will be the distance? So, this time, let us take this time tau, relaxation time. So, it will travel this distance, right. So, velocity. So, this now this velocity whatever now I am talking, this is the drift velocity, and that velocity is one can drift velocity one can write that s, the distance travelled by time tau. Okay. So, this velocity is drift velocity. So, s is known, A is this, tau is this. So, now in terms of this other parameters, okay, one can find the drift velocity. So, drift velocity one can find out. So, I think I will continue this class in next class. Okay. So, here let me stop. Thank you for your attention.